Hey Team Bio, welcome to your homework about enzyme denaturation, where we're going to talk about what happens when enzymes fall apart and why. Okay, so today in class, we added hydrogen peroxide to the enzyme catalase, which is found in liver, and when we did so, we didn't see this, but we knew the enzyme was binding the substrate in the active site. It was changing shape slightly, and when it changed its shape, it catalyzed this reaction, and the products were water and molecular oxygen, a gas. So we saw fizzing. However, there were a series of experiments where when we added hydrogen peroxide to the liver, we did not see any fizzing, or we saw limited fizzing. And the reason for this is because the enzyme denatured. Okay, what does that mean? Well, you all know, here's actually an image of a schematic showing us the catalase protein. So this is catalase. And catalase has a very specific shape that it folds into. As you can see here, there are a few alpha helix structures. So these are all alpha helices, and they are held in place by hydrogen bonding. And then here is a beta sheet right here, again, held in place by hydrogen bonding. And oh my gosh, I should be better like Kate, who was using the swirly, these dots, dotted line. Okay, here we go. This is going to be much better. Ooh, oh no, it's not very good. Oh, maybe this is too big. Yeah, here we go. Dotted lines showing our hydrogen bonding, holding our alpha helix and our beta sheets in place. Ta-da! Like so. Okay. Excellent. Now I'm going to go back to solid. Okay, so here we have an example of a beta sheet. Here is an example of an alpha helix. And when catalase is folded in this manner, it has an active site. I actually believe the active site is over here. And it can catalyze the reaction, decomposing hydrogen peroxide into water and oxygen. However, if it denatures, this means it goes from being a folded protein to a long straight chain, a primary structure protein, which we don't even call a protein, we just call it a polypeptide. Well, there are a couple of different things that can cause a protein to denature. Anything that is going to break these H bonds holding together the structure is going to result in a denatured protein. And so, as you know, a hydrogen bond is an interaction between a slightly positively charged hydrogen in one structure that is associated with a slightly negatively charged oxygen on another structure. So anything that's going to interrupt this bonding, this hydrogen bond, is going to denature the protein. So here are a couple different things that can disrupt this hydrogen bonding. One is changing the pH. The pH of a solution, if you have an acid, this means that you have increased the concentration of free hydrogen in solution. So if there's a lot of free hydrogen just beep-bopping around in the solution, it means it can come in here, swoop out, and bind with this oxygen instead of a hydrogen over here. So high concentration of hydrogen in solution is going to swoop into some of these hydrogen bonds and break the intramolecular bonds that we have going on here. The same thing is true of a base. If we have a basic solution, this means we have a high concentration of hydronium ion, OH minus, which also can swoop into this bond and interact with the hydrogen side, the slightly positive side of the bond. So a strong acid, like you saw when we added hydrochloric acid to our solution, we saw the enzyme stopped catalyzing its reaction. It's because it fell apart. The same thing would be true if we added a strong base. Another thing that could disrupt hydrogen bonding is adding lots of ions. So, for example, if we had a really salty solution, we would have a bunch of sodium and chloride ions in solution. And if we had a bunch of sodium and chloride, this sodium could swoop in here and break up this bond between a slightly positive hydrogen and a slightly negative oxygen, and the chloride would do the same thing, but it would want to interact with the slightly positive hydrogen. So a really salty solution can also denature a protein. And we didn't do that in class, but it is also true. The last super common thing to denature a protein is to change the temperature. So when the temperature is really hot, then hydrogen bonds break. And when the temperature is really cold, we freeze hydrogen bonds. Okay, I'm going to put a little extra asterisk next to cold. So when the temperature is hot, hydrogen bonds break. And this process, when we break the hydrogen bonds and we denature the protein, this is irreversible. Oops, I think this is an S-I. When the hydrogen bonds are broken and they're gone, that's it for our protein shape. However, heating up a protein will destroy it irreversibly. When you freeze a protein, these hydrogen bonds actually freeze in place. And so the ability of the enzyme to change its shape is compromised. It doesn't shift and bend as well because these hydrogen bonds have really firmed up, not allowing this enzyme to flex anymore. However, if you heat the enzyme, if you warm it back up without getting it too hot, you will unfreeze the frozen bonds and it will start to work and flex again. So part of the reason why we saw a first slow reaction when we added the hydrogen peroxide to a frozen liver was because at first these hydrogen bonds were frozen into place, so we saw just like tiny little fizzy bubbles. But then this is an exothermic reaction, so every time it runs, it heats up the reaction, the enzyme, a little bit more. So we quickly thaw out the enzyme by running the reaction over and over again. So you start out with these tiny little fizzy bubbles, and then pretty quickly the enzyme heats up because this reaction is releasing energy, and voila, we start to see a faster and faster reaction and bigger bubbles as time goes on. Okay, so these things can, these four things can irreversibly change the shape of an enzyme. However, freezing an enzyme only temporarily puts it out of business. But if you warm it back up to its typical temperature, then it functions just as you would expect. Okay, that's all.